Hi everyone, my name is Dr. Paul Kerstetter, and today I'll be talking about how to double a voltage using the Dickson charge pump. The simple circuit uses just two capacitors, two diodes, and two voltage sources. In this video, you learn how the circuit achieves voltage doubling, how to derive the result mathematically, and I will simulate it in LTspice. Let's get started. This is the presentation, voltage doubler circuit, the Dickson charge pump. The Dickson charge pump circuit is shown in the slide. If we set Vin to 1 volt and use a 1 volt pulse train for the clock, the output VO will eventually reach 2 volts DC. I say eventually because it takes several clock pulses for the voltage to settle at that level. It may not be immediately obvious, but the circuit has twice as many states as there are clock pulses. However, there are only three distinct topologies. The first topology is shown in the slide, and it also represents the first state. In this state, both C1 and C2 develop a 1 volt charge through the Vin source, which is set to 1 volts. Note that the diodes have been replaced by shorts and the clock voltage is at 0 volts or ground. The slide shows the second topology corresponding to state 2. In this state, the clock has risen from 0 volts to 1 volt. Notice the initial conditions on the capacitors. They carry the charge developed in the first state. Since C2 had a 1 volt charge across it in state 1, and its negative plate is now raised from 0 volts to 1 volt by the clock, we would expect the top plate of C2 to reach 2 volts. However, the positive plate of C1 is only at 1 volt. Assuming the capacitors are equal, the voltage will settle exactly between 1 volt and 2 volts. That is at 1.5 volts. Thus, VO will be 1.5 volts. In the third topology, corresponding to the state 3, the diode acts as an open circuit, allowing the initial 1.5 volts on C1 to remain. Meanwhile, C2 develops a 1 volt charge. The slide shows the second topology again, this time in state 4. The clock has risen from 0 volts to 1 volt. Notice the initial conditions on the capacitors. They reflect the charge developed in state 3. Since C2 had a 1 volt charge across it in state 1, and its negative plate is now raised from 0 to 1 volt by the clock, we would expect the top plate of C2 to reach 2 volts. However, the positive plate of C1 is only at 1.5 volts. Assuming the capacitors are equal, the voltage will settle exactly between 1.5 volts and 2 volts, or 1.75 volts. Thus, VO will be 1.75 volts. This process of alternating between topologies and gradually adding charge to C1 continues with each clock pulse. This is why the circuit is called a charge pump. Eventually, VO will reach 2 volts. For the mathematical derivation, we'll focus on topology 2, state 2, as shown in the diagram. The clock voltage, V clock, will be treated as a step response rather than a full pulse train, essentially representing the first pulse of the train. First, let's review some basic math. In the voltage derivation, I will model the clock pulse train using a step function. This step function is defined on this slide, along with its time integral, which evaluates to 1. The current flowing into or out of a capacitor plate is related to the voltage across it by the equation shown on the slide. For a positive dV dt, the current flows into the positive plate of the capacitor, and for a negative dV dt, the current flows out of the positive plate. The current flowing into the VO node must equal the current flowing out of the VO node. This is a fundamental rule of circuit analysis. The slide shows the equation that expresses this relationship. Since VO is increasing, we expect current to flow into the positive plate of C1. At the same time, the voltage across C2 is decreasing, so we expect current to flow out of the positive plate of C2. Integrating both sides of the equation from the previous slide and solving for VO0 plus yields 1.5 volts. Recall that VO0 plus is the output voltage immediately after the step response rises to 1 volt. Also note that the initial conditions for the capacitors are present in the derivation. For example, VO0 minus equals 1 volt. Because the step response represents only a single pulse in the clock pulse train, solving for VO would need to be repeated for each entry into topology 2. Instead, it is more practical to use a simulator such as LTspice to observe the resulting waveform for VO. The simulation results for the voltage doubler are shown on this slide. You can see that the first step reaches 1.5 volts, exactly as predicted by the mathematical analysis. Eventually, the waveform settles at twice the input voltage in the simulation. That's all for now. I hope you enjoyed the video. If you did, please like it and subscribe to the channel. Stay safe, and I'll see you in the next video.